Welcome to the Japan CCS Forum Technical Seminar. I am Yasuo Murakami, Senior Business Development and Engagement Lead of Global CCS Institute Japan Office. The Global CCS Institute is an international think tank whose mission is to accelerate the deployment of carbon capture and storage, vital technology to tackle climate change and deliver climate neutrality. As part of this mission, we have been hosting the Japan CCS Forum annually since 2015 in Japan. In previous forums, we have disseminated the latest information on CCS projects, progress, policies, and technologies worldwide. According to the Global CCS Institute's flagship report, Global Status of CCS 2023, published in November 2023, there were 392 CCS projects worldwide, representing a 102% increase compared to the previous year. This momentum is largely attributed to strong policies in North America and Europe. Considering these developments, the Institute has decided to focus on various technologies related to the CCS value chain and specific challenges at each stage, and to provide a platform for information sharing and discussion, as the Japan CCS Forum Technical Seminar. The CCS network, also so-called Hub and Cluster Project, would create economies of scale by sharing common infrastructure, which will improve efficiency in the CCS value chain. We recognize there are three methods are currently being considered for shipping liquefied CO2, which forms the backbone of the CCS value chain: EP, elevated pressure, MP, medium pressure, and LP, low pressure. We are very pleased to have representatives from Toyota Corporation, Nippon Yusen Jura Kaisha NYK, and Knutsen NYK Carbon Carriers AS, who conducted qualitative and quantitative comparisons of three methods as speakers. And in this seminar, this is our pleasure to welcome PACE CCS, a consulting firm providing services to CCS projects worldwide, to share their insights with us. Now, as an opening speech, we are delighted to welcome Mr. Tsutomu Yokoyama, Executive Officer of Nippon Yusen Jura Kaisha, NYK. Mr. Yokoyama, please.
Thank you for your kind introduction. And thank all of you for coming to this meeting despite of your busy schedules. I am also grateful to be able to give this opportunity to speak to you. I would like to thank the Global CCS Institute as organizer, and JOGMEC, RITE, JCOAL, and Japan CCS as supporters. The reason we started today's meeting in the late afternoon is to accommodate participants from Europe, whereas leading are in CCS, making it easier for them to join. We are glad to hear we have received registrations from 338 companies, totaling 720 registrants in total. This turnout underscores the strong interest that everyone has in today's session. Today's theme is a comparison of three methods through the CCS value chain. The value chain consists of liquefaction, temporary storage, loading, marine transportation, heating, boosting, and injection. As a shipping company, while we could discuss the transportation aspect, focusing solely on that would be incomplete. So we have conducted a comprehensive comparison of the three methods across the entire value chain in collaboration with Toyota Corporation. By quantitatively evaluating the pros and cons of each three method, we were able to identify specific numerical data. We are delighted to present it to you. While our company can accommodate all three methods, we have been considering determining which is the most appropriate way. However, through this study, we have gained significant insights. Moving forward, we aim to further strengthen collaboration with Toyota Corporation and stakeholders within the CCS industry, fostering ongoing dialogue. Finally, I hope that today's event will provide valuable insights for all CCS stakeholders. Thank you very much.
Thank you very much, Mr. Yokoyama. We are delighted to welcome Mr. Kimiho Sakurai, Vice President, Division Director, Business Development Division, Toyota Corporation. Mr. Sakurai, please.
Thank you very much. I am Sakurai, Vice President and I-Vision Director of the Business Development Division of Toyota Corporation. I am grateful to meet you. Thank you very much for taking part in this event despite your busy schedule. As Mr. Yokoyama mentioned earlier, NYK, Toyota Corporation, and KNCC have jointly conducted a qualitative and quantitative study of the whole CCS value chain. We want to express our gratitude to the Global CCS Institute for allowing us to present our study's results. We also extend our heartfelt thanks to JOGMEC, JCOAL, RITE, and Japan CCS for their support. Since JOGMEC established the advanced CCS projects last year in 2023, large-scale CCUS projects involving collaboration between multiple companies have been initiated at various locations. However, amidst variations in the volume of CO2 liquefaction and transportation in each project, our company needed more explicit criteria to determine the most suitable liquefaction method. Against this backdrop, we commenced a comparative study of CO2 liquefaction methods in collaboration with NYK last year. The conclusion drawn from our research is that each method has its pros and cons. Adopting the optimal method for projects to be implemented by 2030 is imperative to achieve carbon neutrality by 2050. Moreover, enhancing the maturity of each technology is crucial for obtaining appropriate options for subsequent projects. The CCS value chain will only be implemented with the collaboration of every company involved. In this study, we integrated our expertise in onshore facilities as a comprehensive engineering company and NYK's expertise as a leading shipping company. Through today's presentation, we hope to gain the support of companies, including emitters and other stakeholders, for our company and NYK's future endeavors. We welcome discussions with such companies and look forward to expanding our collaboration. In closing, we hope that today's presentation will contribute to the smooth introduction and early societal implementation of CCS in the future. Thank you very much for your attention.
Ladies and gentlemen, we would like to move on to the presentations. NYK and Knutsen have jointly equity investment into Knutsen NYK carbon carriers, as has its unique method of EP, as well as LP and MP in transportation. We will have the CEO of Knutsen NYK Carbon Carriers AS, who will explain to us the outline and challenges of 3 different approaches. Please.
Thank you very much. Good afternoon to those of you who are here, and good morning and perhaps good night to those of you other places in the world. I'm very pleased that we are able to get such a big participation here today. And somebody mentioned more than 700 participants, which I think is very impressive and also tells a lot about the overall attention that CCS, and in particular this very special topic, 3 modes of CO2, is gaining these days. Thanks to Global Carbon Capture Storage Institute for hosting this conference. And of course, thank you very much to Toyota and to NYK, and also to PACE for contributing to this event. For us, KNCC, this is a very important study that has been done. Obviously, we are offering elevated pressure as one mode of transporting CO2. We're also offering mid-pressure and low pressure, but we cannot give up on this elevated pressure because it makes so much sense from a technical point of view and from a commercial point of view. And I think that that is one of the, you will also see today why we are continuing to pushing all this. Next, sorry. I think, yes. I think it is very important when we're discussing CCS and also which mode of CO2 we will carry the stuff in. It's very important that we remind ourselves what this is all about. CCS value chains are a new industry, and it is extremely important that we all share a common understanding of what this takes. First of all, we're dealing with a cargo or a product that has absolutely no value. people want actually to get rid of this. And that means that we are in the waste management business. And everybody should know that if you're dealing with waste management, then you have to do this as cheaply as possible. And one of the ways to achieve low cost is scale. So waste management needs scale. So this is also a scale game. And thirdly, this is extremely capital intensive. I think we haven't still seen the total cost and the consequences for those who will pay for this, consumers and governments and businesses. And it comes with a cost, a huge cost for a product that doesn't carry any value. So we need to have a sharp focus on cost. And finally, that is also a very important thing to note here, is that this is long-term commitments. You cannot start the CCS value chain today and close it in 3 years' time. It doesn't make sense. So this is a very important part of the globe's greenhouse gas reduction objectives. And so this is something that we establish for the long game. From a shipping perspective, that's obvious, but it's also from the capturing or the emitters who would have to realize this, and also the storage providers. Very important. And I think also one important thing to note here is that we are focusing primarily for the time being on technical matters on this case. But I think we owe the society and the consumers that will pay for this, that we also start to highlight on the cost side. Because it may become a shock for many people when they realize the cost of handling or capturing CO2 and handling it almost in a value chain. Next. The following presentation is divided in 3. We are focusing on first of introducing KNCC, Knutsen NYK carbon carriers. Then we are looking into the part 2 is sort of a qualitative assessment of the 3 modes of CO2, low pressure, mid pressure, elevator pressure. And the third part of the presentation is focusing on where we are in KNCC when it comes to technical development. I think the key messages that we would like to give, and I hope that you will sit back with that reflection after this presentation, is that we in KNCC, we are NYK's and Knutsen Group of Norway's key gateway of CO2 shipping. And secondly, that we are also offering elevator pressure technology for handling CO2, but we are also including mid-pressure vessels and low-pressure vessels in our offering. When it comes to part 2, I think it's very important that we see that we can show you that elevator pressure has certain benefits that is unique compared to mid-pressure and low pressure. But at this stage, there are also quite a lot of uncertainties because nobody has actually built this yet at scale. So the findings in the study is very interesting, but still needs more work in order to know which way to go. The third point that I'd like you to sit back with when we are finishing here is that Knutsen NYK Carbon Carriers is a reliable company that can offer all 3 modes of transportation. And actually that we have what we in the CO2 geek world refer to as deep knowledge about CO2, which is of extreme importance to us as a company when we are discussing with our customers on a global basis. Next. And next. I just wanted to mention a few things about our owners. We, as KNCC, we are a startup company. We are 5-6 people working on the western coast of Haugesund, where we have gotten till today would have never been possible if we didn't have the strong support from NYK and Knutsen, our shareholders together. And I think it's quite interesting to see that what we have been able to get involved in sitting on the western coast of Norway in a tiny little village called Haugesund. And we are primarily working globally and we don't put much efforts into marketing. But the whole elevator pressure ambient technology has gained a lot of attention on a global basis. And I think that has come when people realize that this comes with a cost, the whole CCS value chain. And that cost is too much perhaps also, so they need to look into new ways of handling all this. In addition, we are shipping experts. We know how to serve a value chain. And when it comes to these kind of value chains that we're discussing here today, I think the 2 points of regularity and frequency are extremely important for a shipping company that wants to serve such a value chain like this. Next. This is setting out our scope of business. The most important thing with this illustration is really that it shows that we have a very holistic approach to what we're doing. We're trying to understand the whole value chain every time we're discussing or working on a project. More in detail, when it comes to our offering here, we can load CO2 from into our vessels, either from offshore or onshore. We can discharge the CO2 directly from a vessel into a reservoir, or via floater into a reservoir, or to a terminal onshore that again pushes the CO2 in the pipeline into the reservoir. We have sort of also developed onshore tanks for the elevated pressure value chains, enabling us to offer the whole of sort of the full logistical part of the value chain, which is quite important. And I think also it should be highlighted that our customer base, or prospective customer base, is today the companies on the left-hand side, the emitters, the ones who will pay for this in the end. We are also, of course, dealing with the storage providers. And I think it's fair to say that the division between our customer base is now only half-half. Somebody's having the microphone on here. Further, our offering, as I said, we can do elevator pressure, mid-pressure, and low-pressure vessels. And we are quite actually open to what vessels that we will offer to the various CCS projects. We see, however, that elevator pressure makes sense in certain settings, and in those settings we will push that. For instance, when it comes to offshore solutions, we are only offering elevator pressure. We don't think that we think that that would be the best technical and cost optimal solution. Next, please. So in that respect, we are the only company that is offering vessels offering the full range. We're offering elevator pressure, mid-pressure, low-pressure vessels. And we have what we call terminal-to-terminal vessels, or direct injection vessels, offshore vessels, for elevator pressure. And when it comes to mid-pressure and low-pressure vessels, we are dealing with terminal-to-terminal vessels for both those two modes. And of course, the tanks for mid-pressure and low-pressure are sort of, I wouldn't call it standard sea tanks, but it's sea tanks. And for our elevator pressure vessels, we have our own cargo tank cylinders storage system. And then you can see on the bottom here that the illustrations of how the vessels are supposed to operate. And it's not that, it looks very simple when you look at these drawings here. It's not that simple in practice, we think. But from an illustration point of view, these are sort of the three modes three alternatives that we are offering. If we go to the next slide, then we can, that is setting out the offering when it comes to sizes of vessels. We are offering 20 to 80,000 tons carrying capacity when it comes to elevator pressure. Medium pressure, we have an upper limit on 20,000 tons. And when it comes to low pressure, we think that there's for the time being at least, an upper limit on 80,000 tons. Then the first vessel order will probably be mid-pressure vessels, where the design is more mature and, for instance, for low pressure. Next, please. This is an illustration of how we the containment system for elevated pressure that we are offering. It seems it can look complicated from the slide, but we have had two things on our mind when we have designed this. It has to be cheap, and it has to come with a low operational risk. And then you can say, oh, there are so many pipes and there's so many connections and all that. We have developed and designed all this to be sort of in a plug-and-play basis. And we have been looking into every detail with the classification company and with other engineers and design companies. So we are 150% certain that this system here, with all the benefits it will offer, it's also a safe operational technical system that will work. Next. And of course, we also realize that if you are offering elevated pressure vessels, you need to offer also elevated pressure onshore tanks, which we have illustrated here. We have designs for onshore tanks when it comes to simple terminals. We have floaters, we have barges, and we have floating injection units as well. So the offering when it comes to elevated pressure is quite unique and wide in that respect. So before I'm moving on to part two, I want you to keep in mind, or I would like you to remember two things. KNCC, we as a company, we're offering all modes of handling CO2. And that we regard the cost side of this as one of the key drivers, probably the most important thing to have to be in place if this CCS business is going to fly. Next. The following slide sets out sort of the key parameters when it comes to comparing elevated pressure, mid-pressure, and low pressure. We have divided that into 5. It's operation and risk matters. It's cost and energy consumption matters. It's net transporting volumes on the vessels. It's how the CO2 behaves in the various modes. And it's also a bit about the tanks that will be used for handling the various modes. This slide is setting out sort of basic information. It only says that when you are dealing or deciding which mode of CO2 that you're going to choose, you need to have some matters on the front of your mind when it comes to operation. And that is, of course, that you need to have a buffer or to be on the safe side when it comes to dry ice risk formation of the CO2, the triple point. That is extremely important. Secondly, it's the matter of impurities that we will have more from Matt afterwards. Pace, where elevated pressure and mid-pressure and low pressure are sort of how they are enabled to handle impurities in the CO2. And CO2 specification is a very hot topic in our little society these days. And Non-Light had their online webinar regarding their new required specification for CO2. That was, I think it was even more popular than this seminar today. So it just tells us all that the CO2 specification is a really, really important matter that needs to be observed. Next slide, please. When it comes to energy consumption, we have looked into sort of liquefaction and storage and transportation and injection to the wellhead. And from that point of view, we are not surprised by this, but it seems that we have found that elevated pressure across the value chain is less energy intensive, i.e. less cost intensive than the other modes. in many ways, that goes without saying, because apparently we use a lot less energy by keeping the CO2 at ambient temperature. But finally, we have had a study now evidencing these facts for us as well, and that is of big importance to us. And I think, again, it boils down to the cost side here. If you are contemplating building a CCS value chain, you need to take these kind of findings into consideration. Next slide, please. Yeah. We all know that there's no free lunch in the world, so even elevated pressure has its disadvantages, and the most important one is actually the density. Density of elevated pressure compared to mid-pressure and low pressure is less, so that means that you need bigger vessels, or you need to do more rounds to handle the same volumes of CO2 compared to low pressure and mid-pressure. However, there are some mitigating factors, but the overall conclusion doesn't change. But there are some mitigating factors, and that, for instance, is the required heel in the tanks, i.e. heel is the sort of required amount of CO2 that you need to keep in the tanks after discharging. And the heel requirement for elevated pressure is far less than for mid-pressure and for low pressure. And this is related to the need to having the tanks at a certain cool temperature when you're going to load the CO2 on board the vessel again. But as I said, it makes the picture slightly less worse for elevated pressure, but the overall conclusion is that the density for elevated pressure is less than, also including heel, is less than for the other two modes. Next, please. I'm coming back to this afterwards, but in Haugesund, where we have our office, we have also built a CO2 test rig, where we have stored CO2 in the tank, in our tank system for several months. And we have discovered two things, and sort of, I wouldn't say it was a surprise, but we were happy to have it confirmed. And that is that when you keep the CO2 in the cylinders, even when the outside temperature is fluctuating, the CO2 is quite stable and moves along with outside temperature. And if you look at the black diagrams here, they are quite, it's a bit difficult to see on the screen, but it shows how the CO2 is very stable over time. This time scale here is over 2 months. So that means that, for instance, we don't have any boil off from the tanks, and we don't have a need for re-liquefaction when we are carrying the CO2. That is a definitely plus. Next. The final part of this section is about the cargo tanks. And we have set out an overview here, showing the material the tanks are made of, and other specifications. This is still a new business for the tank makers as well. And now the first non-light vessels tanks have been lifted on board the non-light vessels at Dalian shipyard in China. So obviously that has been completed. But it's still also, and then we know that there are some low pressure tanks that will be built to be installed on vessels going forward. But also, of course, when it comes to putting low pressure tanks, for instance, on shore, that comes with certain challenges, both in production and construction, and also timing wise, there are some challenges. But when it comes to the tanks in itself, I think it's fair to say that it's still technology that needs to be further developed, but we will get there in the end. So summarizing part 2 then, I hope that you have understood that there are certain pros and cons with the 3 modes of CO2. And the conclusion when it comes to which mode you should use is really dependent on the project specific specifications that you're dealing with. And the most important thing is that at least we are evaluating those 5 parameters that I have discussed now. I will quickly start to summarize with conclude with part 3, and that is just a quick overview of our technical development over the last year or so. So yeah, next slide. Sorry, I forgot. Next slide. And one more next. Here we are. This is where we are from a technology point of view. We have our general approval for ship application for the CTC system for elevated pressure in place. We have access to AIPs when it comes to low pressure and mid pressure vessels. We are actually also discussing specific projects when it comes to mid pressure and low pressure with shipyards these days. So that is quite interesting to see the progress of that. And further, we have done what we refer to as HACCP, which is sort of identifying all major risks related to our systems in order to verify that this is acceptable within a sort of risk frame system as well. Next slide, please. And this is the test rig that I referred to earlier. On the left-hand side of the picture here, you can see the illustration from what we see on our laptops when we are looking into the status of the rig. The picture to the right-hand side is one of our colleagues who is actually testing the leakage of CO2 from one of the tanks. The third picture is the rig in itself. It seems quite simple. And on the left-hand side of that picture, you see a white box. That's our visitor center, very famous visitor center. And on the right-hand side, there's a storage tank, and the two cassettes in the middle, that is actually the test rig in itself. We have completed phase 1 for this rig. And now we are in the planning and started to do phase 2 testing, which is focusing on corrosion and leak testing. And phase 3, we are aiming to look into how CO2 will react to impurities. So this is quite interesting from an industry point of view. And for us as a company, it's also quite interesting because we are learning a lot, and we foresee also to use this facility to train crew for vessels going forward. And this will provide sort of an excellent way of educating all the crews on the CO2 vessels that will be needed in the future. And that is quite a lot. So in sum, I think it's fair to say that due to this test rig, due to the engagement with 40, 50, 60 projects, it's fair to say that we as a company has developed a very deep knowledge about CO2 that we try to use as best as we can in all new projects that we are looking into. This is, of course, also to show you that we regard and the market regards elevated pressure as a viable option, as a third mode of handling CO2 on board. And we have, if you show the next slide, please, we have been reaching out to the companies that we have been working with over the last 2 years. And this is a few of them. I would say it's not half of them, but around half of the companies that we have been engaging with. And it's to us, it's a big pleasure to see that there are so many companies that are looking into elevated pressure for real, and that they see the benefits of working and developing elevated pressure as a third real credible alternative. I really hope that you will be of the same opinion after this presentation. And if not, please call me up. Please approach me after this one, and then I will convince you. Thank you very much for the attention.
Mr. Anders, thank you very much. Now we are moving on to the next presentation. we will have a presentation about the comparative study results regarding EP, MP, and LP via the CCS value chain from Chiyoda Corporation and NYK. NYK has been leveraging its extensive experience in ocean-going shipping to continue creating new value through decarbonization efforts. Since its early period, Mr. Takahiro Rokuroda, Deputy General Manager of the Green Business Group, has been involved in NYK's decarbonization efforts. Drawing on his wealth of experience, he will explain the comparative study results for the three methods of liquid CO2 transportation throughout the CCS value chain. Chiyoda Corporation, a general engineering company, actively engages in initiatives related to implementing the CCS value chain towards achieving a carbon-neutral society. Mr. Atsushi Tamagawa, General Manager of the Gas and LNG Process Engineering Department, is advancing the construction of technologies such as CO2 liquefaction plants based on his expertise in liquefied natural gas. Building upon this expertise, he will explain the comparative study results for the three methods of liquid CO2 transportation throughout the CCS value chain and the recommendations derived from those results. Mr. Tamagawa and Mr. Rokuroda, the mic is yours.
I am Tamagawa from Chiyoda Corporation, and I am Rokuroda from NYK. Thank you very much for your participation in the meeting. It is a great honor for us to present to all of you here at the venue and to many participants online. We are truly grateful to GCCSI and all other parties for organizing this meeting. Now, we will proceed with our presentation on the quantitative comparative study results of the three CO2 liquefaction methods, LP, MP, and EP, through the CCS value chain. Next slide, please. Before the presentation, we want to note that we used the cost data, such as capital expenditure, CapEx, and operating expense, OpEx, which were analyzed based on reliable data available at the time of the study. Please consider this information as reference. Next slide, please. Here is the content of today's presentation. In Item 1, we will again explain this study's purpose. Next, in Item 2, we will introduce the study's premises. In Item 3, we will explain an overview of the configuration of each process in the entire CCS value chain. Based on these, from Item 4 onwards, we will present the results of the quantitative comparative study conducted in this session. Regarding the study results, we will present two cases, domestic transportation and international transportation. Finally, we will organize future actions for social implementation and conclude our presentation. Next slide, please. Here is today's agenda. In this study, we are examining the CCS value chain with the premises of bulk transportation involving liquefaction. The term CCS value chain refers to a series of processes including the separation and recovery of CO2 from emission sources, followed by liquefaction, temporary storage at the receiving end, transportation, and temporary storage at the receiving end for retention. Based on the characteristics of LP, MP, and EP, we aim to comprehensively evaluate the entire CCS value chain. Indeed, discussions have been held on the characteristics, pros, and cons of each liquefaction method for various processes such as tanks and transport ships. However, we believe that evaluating the CCS value chain as a whole is crucial. This aspect has not been extensively explored before, so we would like to introduce it through this presentation. We hope that understanding the characteristics of each method will serve as valuable reference information for your considerations in future business. Additionally, in terms of the evaluation criteria for this comparative study, we have organized comparisons of CapEx and OpEx for each method at each stage, as well as identified necessary actions for societal implementation moving forward. Next slide please. Firstly, to capture CO2 from the initial emission source, we assumed that CO2 would be recovered from combustion exhaust gases using amine chemical absorption. Regardless of the liquefaction method, we did not include this stage in this comparative study as we consider it to be the same. Next, a recovery volume of 2 million tons per year was assumed for liquefaction. Additionally, for the liquefaction process, we thought of an external refrigeration process using propane for this study. Furthermore, for CO2 transport ships, we considered two cases, domestic transport and international transport. For domestic transport, we assumed a distance of approximately 1,500 kilometers from Osaka to Hokkaido. We regard it as a long-distance transport of roughly 5,600 kilometers from Japan to Australia for international transport. The capacity of each transport ship was assumed to be 20,000 cubic meters for domestic transport and 40,000 or 50,000 cubic meters for international transport, depending on the method. Additionally, for the transfer conditions during the final storage, wellhead, after primary storage at the receiving end, we set conditions of 10 MPa gauge and 20 degrees. The storage process is assumed to be the same regardless of the liquefaction method, and we excluded it from this study. To summarize, this comparative study of the three liquefaction methods focuses on the stages following liquefaction: primary temporary storage and transport on the shipping side and temporary storage on the receiving side. Though it may seem detailed, the primary storage on the receiving side includes pumps for pressurization and heaters for heating, which we will explain in more detail later. Next slide please. Next, I will explain the cases considered in this study. While we may repetitively explain, the conditions of MP, LP, and EP on the left refer to the temporary storage at the loading end and temporary storage at the receiving end, as well as the operational conditions for each transport. Additionally, as mentioned in the assumptions for this study, we considered two cases, domestic and international transportation, for the three liquefaction methods. Regarding international transportation, due to the difficulty of increasing the size of the vessel for MP, we conducted a comparison of LP and EP for international transportation in this study. Furthermore, as highlighted in the comparison of the three methods in the KNCC presentation, the difference in density at CO2 liquefaction is highlighted as a feature of each method. The table includes the liquid densities of CO2 for each method. It was found that there is approximately a 10% difference between MP and LP and approximately a 20% difference when comparing EP and LP. From the perspective of transporting mass relative to a fixed dosage, LP, with its higher liquid density, can carry more. In this study, to compensate for this difference, in consideration of EP, both for domestic and international transport, we increased the capacities of transport ships and tanks significantly compared to the remaining two methods. While it may be conceivable to adjust the number of vessels or the number of voyages while keeping the ship's capacity the same, for this study, we adjusted the capacities of transport ships and tanks while keeping the number of vessels constant. Additionally, considering that the tank capacity of temporary storage may vary depending on project conditions, for this study, we set the storage capacity of tanks at 10% higher than that of transport ships. Please proceed to the next slide. Next, let's discuss the assumptions regarding costs. This slide will mainly focus on onshore tanks. In the results of this review, CapEx or OpEx will be presented in terms of the cost per unit of CO2, unit cost. CapEx includes only material and construction costs. As for OpEx, it considers only electricity costs, and for details on the electricity cost settings, please refer to the slide. The equipment using this electricity mainly includes compressors, pumps, electric heaters, etc. While there may be various other utilities, for this review, we assume a constant utility consumption regardless of the three methods. Now, let's move on to the next slide, please. Here is an explanation of the estimated cost for the vessel. Similar to the explanation provided by Mr. Tamagawa regarding onshore facilities, we are also making calculations for expected costs to a certain extent, but for vessels. In terms of CapEx, we have incorporated estimates of the reasonable prices for each of the three types of ships through consultation with shipyards, although there are differences among them. However, these estimates have not included interest rates and various incidental expenses. On the other hand, concerning the OpEx of the ship, there are various costs such as crew costs, labor costs of crews on board, costs of different supplies, costs of lubricating oil, dock costs incurred when entering the dock, P&I insurance, and expenses for ship management. Additionally, during the ship's operation, we have also included related travel expenses, such as port costs when calling at ports. As for costs that significantly deviate from our assumptions, these would be the interest on the initially proposed capex and other miscellaneous expenses. Next, please. Regarding the size of the vessel, first, the blue square area highlighted in this table represents the numerical values for the ship type intended for domestic transportation. Liquid density differs slightly among the three modes, with LP and MP being 20,000 cubic meters. As for EP, it is assumed to be 10% higher at 22,000 cubic meters. Although this only partially clears the difference in liquid density, it is considered to be very close. The vessel depicted here can be tailored and modified in various ways. It is an EP carrier. LOA stands for the overall length of the vessel. Beam refers to the width of the vessel. EP is slightly larger than the other two types of ships, mainly due to the lower liquid density and increased volume. This indicates the draft, water displacement. There is little difference regarding this. As we will explain later, an EP vessel carries many cylinder tanks, making it generally heavier and prone to deeper drafts than the others. However, the actual density of CO2 loaded as cargo is lower, meaning it is lighter than others. Therefore, when the EP vessel is loaded with CO2 and launched, the final drafts for all three types are expected to be similar. Again, according to the specifications of each port and operational profile, individual consultations will be required during implementation. As for overseas shipping, 40,000 cubic meters for LP. Considering the 10% increase in EP, LP and EP are about 20% different. Additionally, KNCC had considered 50,000 cubic meters before this study, so we have set it to 50,000 here. As a result, LOA and beam become considerably larger, but we aim for a minimal difference in draft when depicting such ships based on these materials. Next slide please. In this slide, I will explain the outline of the considerations for each process in the CCS value chain, including the liquefaction process. The left side represents the liquefaction process, which consists of compression, dehydration, impurity separation, and liquefaction, elements common to all three liquefaction methods. Regarding the transportation conditions of liquefied CO2 for the storage, the facilities on the right side are added as ancillary equipment for each method, but their overall contribution is minimal. One of the characteristics of this liquefaction method is the refrigeration equipment highlighted in the red box. As qualitatively described, refrigeration equipment consumes more energy at LP and decreases energy consumption at MP and EP, which is also mentioned in the presentation by KNCC's presentation. Please move on to the next slide. Next is an overview of the facilities for temporary storage on the shipping side. A major feature is the configuration comprising storage tanks, loading pumps and arms, and a boil-off gas, BOG, reliquefaction unit. One notable characteristic here is that for LP and MP, spherical tanks are assumed. On the other hand, for EP, we assume the cylindrical tanks known as card-type cylinders, CTC. Another characteristic is that the duty of the BOG reliquefaction unit during BOG is greater for LP, as the temperature difference with ambient air is larger. In other words, there's a tendency for the duty of the LP reliquefaction unit to be larger. Regarding EP, the current assumption is to adopt the CTC tanks in large buildings and manage the air conditioning there. If this management approach is realized, we believe that a reliquefaction unit for use will be unnecessary. Next slide please. Here is an overview of the facilities for temporary storage on the receiving side. The configuration of tanks and BOG reliquefaction units is the same as that of the temporary storage on the shipping side mentioned in previous slide. However, for the receiving terminal, we have added booster pumps for pressurization and heaters for warming towards the upstream. The tank types and features of the BOG reliquefaction unit here are the same as mentioned before. The energy involved in the booster pumps for pressurization towards injection varies with the operating conditions of each method. In this case, the difference with the set pressure of 10 MPa megapascals gauge is largest for LP and decreases for MP and EP. In other words, the energy for LP is slightly higher. Similarly, for warming, the temperature difference with the set operating temperature of 20 degrees is largest for LP. Therefore, it can be qualitatively understood that the energy required for these pumps and heating elements is higher for the LP method. Next slide, please. Let me explain the quantitative comparison results of liquefaction methods, focusing on the CapEx for domestic transportation cases, comparing MP, LP, and EP. The comparison results highlight 2 points. The CapEx of the temporary storage tanks is highlighted in purple and orange, and the CapEx of the transport vessels is highlighted in pink. I will provide detailed information in subsequent slides regarding temporary storage, but particularly for MP, considering requirements such as project duration and the number of tanks, which increases significantly, leading to a considerable rise in CapEx, including construction costs. For transport vessels, qualitatively, in the case of EP, as mentioned earlier, increasing capacity and weight contribute to the increase in CapEx. On the other hand, in the case of LP, the need for nickel ore adoption due to low temperature specifications adds to the material-related factors in CapEx. Considering both factors contributing to the CapEx increase in this study, LP is higher in EP. Evaluating the entire value chain, LP and EP show around a 5% difference, but considering the precision of the estimates in this study, LP and EP are almost at the same level as CapEx. Meanwhile, MP stands out as it has higher CapEx than the other two methods due to the high cost of tanks on both the shipping and receiving sides. Please go to the next slide. Here are the results of the quantitative comparison of OpEx for domestic transportation cases. Similar to the qualitative explanations provided by KNCC's presentation, there are 3 notable characteristics in the comparison results of OpEx this time. As the blue section indicates, the first point concerns the liquefaction process. LP's OpEx is higher due to the significant power difference required during the cooling of the liquefaction. It decreases sequentially from LP to MP and then EP. The second point pertains to the OpEx of temporary storage on the receiving side. As mentioned qualitatively earlier, LP exhibits the highest OpEx due to the energy required for booster pumps for pressurization and heaters towards storage. EP shows the lowest OpEx among the methods, confirming the same trend as qualitatively described earlier. Regarding the OpEx related to transportation, LP is considered advantageous regarding tank capacity, weight, and fuel efficiency. This is reflected in LP having the lowest OpEx in the results. Considering OpEx for each process in the CCS value chain, EP has the smallest OpEx, followed by MP and LP. Additionally, the chart displays the CO2 emissions generated during the liquefaction, storage, and transportation processes, represented as electricity required for liquefaction. This calculation assumes that a base of thermal power generation and LNG are used as fuel for transporting vessels. The results show that CO2 emissions increase sequentially from EP, which has the lowest OpEx, to MP and LP. As this value chain aims to recover CO2, it's crucial to minimize CO2 emissions during the process. Next slide please. In the previous 2 slides, we discussed CapEx and OpEx in terms of CO2 emissions per unit. This slide presents the comparison results of the total CapEx and OpEx. By aligning these two side by side, it's evident that OpEx comprises a significant portion. This aspect aligns with the comparison mentioned during the OpEx analysis, where the sequence is reflected in the total values. In this case, EP has the smallest total value, followed by MP and then LP. This indicates that EP has the lowest combined CapEx and OpEx, followed by MP and LP, respectively. Next slide please. Here, we will explain the comparison results focusing on the temporary storage tanks as introduced in the previous CAPEX comparison. Several points are highlighted. Firstly, it's assumed that MP and LP use spherical tanks while EP uses card-type cylinders, CTC. It's noteworthy that for MP and LP, carbon steel is assumed as the tank material. However, due to safety regulations, if the thickness of the material exceeds 38 mm, request for annealing at soldering is required, making on-site manual metal arc welding necessary. Thus, the maximum tank capacity for MP is set at 900 cubic meters, and for LP, it's 5,000 cubic meters, considering conditions where manual metal arc welding can be accommodated. As a result, for domestic transportation, the tank capacities on the shipping side are 22,000 cubic meters for LP and MP combined and 24,200 cubic meters for EP. To meet these capacities, 28 tanks are required for MP and 5 tanks for LP. Construction costs are represented in days, and the third point from the top indicates the weight when empty. Since EP operates at high pressure, the weight is 2 to 3 times heavier than the other methods, making the material costs the highest among the three. On the other hand, due to the necessity of manual metal arc welding, which does not significantly improve efficiency on site, MP requires welding for 28 tanks, resulting in significantly higher construction costs, making MP the most expensive in this cost comparison. Regarding LP and EP, as explained earlier, the consideration of enclosing CTC in buildings for EP incurs additional costs, making it slightly higher than LP, which doesn't have this requirement. Another highlight is the tank-related construction period. Although we present a range here, assuming on-site crew as a baseline, in practice, the availability of crew and the sequential nature of the work mean that the construction period may significantly lengthen for each MP and LP. While these numbers may vary based on crew availability, it's essential to recognize the challenge posed by these construction periods. Regarding EP's CTC, since there's no on-site welding required, alongside design and civil expressions, parallel production of CTC and transportation for installation could mitigate the risk associated with construction periods, as it eliminates the need for on-site application processes, as confirmed from this study's results. Next, let me explain about international transportation. Please understand that this will be a comparison based solely on OPEX. We're comparing LP and EP in the table on the bottom left. The land function section is the same as the domestic one we discussed earlier. Additionally, the injection side is generally the same as before. The significant difference lies in the pink marine transportation. The main distinction between LP and EP lies in fuel consumption. EP ships are slightly larger, hence, they consume more fuel. Since the distance increases on the route to Australia compared to domestic routes, the fuel load becomes heavier for EP. Therefore, in the case of the domestic transportation outlined by the dotted lines in the upper right, LP domestic is 11.9, Australia is 20.2, EP domestic is 12.9, while Australia is 22.1, all increasing. However, the increase for EP is more significant. Consequently, the difference between domestic transportation is 15.6%, and the difference between international transportation is narrowing down to 10.5%. However, Australia might be the farthest destination when considering Japan as the starting point and looking for overseas storage locations. Therefore, concerning OPEX, EP still has some competitive advantage. Next slide please. When considering challenges for societal implementation, examining the three liquefaction methods within the CCS value chain reveals. Each method is currently being explored based on existing technologies or materials. In terms of development aspects, there are few challenges, as all three methods lack significant technological obstacles. However, regarding operation and maintenance approaches, each method requires tailored engineering themes to be addressed in the subsequent phases of each project. Next please. In this slide, we organize action items for each liquefaction method towards social implementation, as mentioned in the previous slide. Regarding the tanks for MP and LP, issues such as the increased base number of tanks leading to considerations on the tank construction period, securing welders, and cost challenges are raised. One solution is the adoption of pressure vessel type tanks. Also, regarding the loading operation procedure for liquefied CO2, while we believe it is similar to EP, further confirmation is needed. Additionally, regarding transport vessels, MP presents challenges, considering the difficulties in both technology and economics, especially with regard to scaling up to larger vessels. For LP, due to the similarity of conditions to the triple point, there are concerns about dry ice formation. It is crucial to design preventive measures against dry ice formation or to have a design that can promptly respond if dry ice forms unexpectedly. Since operational testing of LP demonstration vessels is progressing, we anticipate finding solutions from there. Furthermore, compared with CapEx, the high cost of LP is a significant issue, so continuous consideration of new materials or certifications for cost resolution remains challenge. Lastly, concerning EP, we identify common challenges, as CTC is common between land tanks and transport vessels. EP still lacks progress in areas such as operational guidelines for CTC tanks and safety philosophies compared to other methods, so further efforts are required. Also, due to the dense arrangement of cylinders, a probabilistic inspection method is deemed necessary. Regarding the tank construction period, while previously EP didn't accrue interest points, it's essential for the realization of EP to establish the supply chain for CTC, including material procurement and fabrication shops, involving manufacturers. Progressing through these engineering themes towards social implementation one step at a time is deemed necessary for the next phase. Next slide please. Lastly, let me summarize this presentation. First, we conducted a comparative study of 3 liquefaction methods regarding domestic transportation. Concerning CapEx, we found that LP and EP are at a similar level, while MP, due to a higher number of tank bases, as mentioned earlier, incurs slightly higher costs than the other 2 modes. Additionally, for OpEx, there's a tendency for OpEx to be higher in EP, MP, and LP orders, particularly due to the liquefaction process and the final pressure boosting process on the receiving end. Regarding international transportation, while it's qualitatively understood that LP has an advantage from a transportation perspective, when considering the entire value chain, similar to domestic transportation, the study results still show an advantage on the EP side. Lastly, the quantitative comparative study results presented today highlight the crucial importance of addressing challenges such as project duration for temporary storage moving forward. We believe it's necessary to consider standards that involve plant owners or tank suppliers to achieve an optimal schedule. And with that, our presentation concludes. Thank you very much for your attention.
We will have Mr. Matthew Healy, the next speaker, as the Managing Director of PACE CCS. PACE CCS is a global leader in the design of CCS systems, with a wealth of experience in many CCS projects worldwide. Matthew has been involved in numerous CCS projects, and will deliver a presentation today on establishing and operating the entire CCS value chain, based on his extensive expertise in upstream design. Now, Mr. Matthew, please proceed.
Thank you very much, and thank you for the opportunity to have the chance to talk today. I have a short presentation, and I think with the 3 presentations we get a full understanding of the question at hand. We've had an excellent review of the qualitative aspects of the 3 different types of shipping. We've had some terrific numbers there, which are of great value to me and my company on the quantitative and cost side of things. And what I want to do is talk about some project experience. PACE CCS, we are a CCS design company. We're based in London, although we've got offices in Malaysia and Houston as well. I'm the managing director, and I wanted to share our experience designing projects that are looking at shipping. And if we go to the next slide, please. Thank you. This is a picture of a fairly typical CCS industrial cluster. We are usually talking about, when I describe CCS design, I talk about the full chain, which is a phrase we've heard many times today. And that is the connecting of a source of CO2 for somewhere to dispose of the CO2. This is the full chain that we're talking about here. Now, this means usually shared infrastructure. Shipping is an excellent example, but we're also talking about pipelines, compressors, and of course, disposal wells. When we design these systems, we need to think about operation. Cost estimates are one thing, but we all know as engineers that design and operation are two different things. This is a brand new industry. There is limited experience, and when we're designing in a brand new industry, we have to consider how these systems will operate. Because while we are sharing new information here, and I'm sure the information I've got to share is new to most people, when we operate these systems, we're going to have operators who are new to CCS. As Anders pointed out, he sees the demonstration unit as an excellent opportunity to teach operators and give them experience. The other thing that we can do as designers is keep things as simple as possible. So if you go on to the next slide, please. I have some, there's a list here which can't be seen on the screen, but this is a list of every operating CCS project around the world. This is from the GCCSI's annual report. So if you don't have a copy of that, I highly recommend you download it. There are about 30 projects in operation right now. But of those 30, all of them are either enhanced oil recovery. And enhanced oil recovery is not CCS. We're injecting CO2 into geological storage, but this isn't waste disposal. This is a commercially driven project that makes a profit. We don't have that with CCS. We have costs that we have to bear to dispose of our CO2. Of the remainder, most of them are pilots. We, of course, have the Tomakomai pilot project in Japan, and there are small projects all around the world. And if we ignore the pilot level projects and the EOR projects, we're left with only two in operation. One of this is Gorgon LNG CCS in Australia. Those of you that are familiar with Gorgon will know that it has had some significant troubles, including a 2-year delay in startup. And Qatar LNG CCS, which is a very similar project to Gorgon, and a project that we know very little about. I certainly can't talk intelligently about it. If someone online or in person has had experience with this project, we'd certainly be interested in lessons learned. None of these are shipping. The only shipping project that's been in any operation is the Greensand project in Denmark. They've had a pilot level injection over a very short period of time. And the lesson here is this is new. We're still learning. And so let's share some of the things that we have learned. If we go on to the next slide, please. Okay, well, we can't see that, but it's a really nice picture showing CO2 coming from multiple sources. All my pictures are from Europe, but they are generic. And what you'd see here is CO2 coming from the UK, from Norway, from Western Europe, and from Northern Europe. And really, this is just another picture of an industrial hub. The project drivers, though, are the same as they are for any major project, and that is cost, safety, and operability. And when we talk about operability, we would like a simple project, please. Now, there are projects that are out there, and they come to the table with assumptions. And what we've learned, and this is really the lesson that I want to put forward, is that those assumptions around shipping, they don't always hold true. What people think their project will look like at the beginning does not end up being what their project looks like. And I've got two case studies, which I can show. I can see on the screens here, the people online can see the pictures, so apologies to those people who are here in person. But if we go to the next slide, and hopefully this one will be a little clearer. Here we go, look at that. So this is not a real project. This is a case study. This is based very closely to a project that we have experience on. So while it's not true, it is based on a true story. This is a fake map. I'm showing blue hydrogen being produced at Pace's office in London. We are not producing hydrogen at Pace's office in London. In fact, we don't do anything practical. We are design engineers, so we're very familiar with our computers and our pencils and paper. What we have here, and this is essentially the project that I'm looking at here, is we have a new blue hydrogen plant. So producing hydrogen and with CO2 capture built into the hydrogen. And then we have dedicated shipping shuttles to an offshore disposal buoy. And that's minimum infrastructure so that you can simply float your ship over to the buoy, inject into your disposal reservoir, and then have 2 or 3 shuttles just going backwards and forwards, taking the CO2 from where it's produced on shore and then taking it offshore to the disposal point. Now, this project made an assumption. They said, we want MP shipping. And we want MP shipping because that's going to be the lowest shipping cost. And also it gives us alignment with Northern Lights. Northern Lights, for those that know the project, is an outstanding technical project. It's also an incredibly expensive one. It is a fantastic project to learn from, and the developers of the project have been exceptionally generous with sharing lessons learned, and we're drawing on a lot of those lessons in this presentation. But the cost of that project is, by inspection, significantly higher than perhaps a project with stronger commercial drivers might end up with. Let's find out what we learned on this project if we go to the next slide. So we looked at this project within PACE, and here's what we learned. I'm a technical person, and so things get technical, and this is a phase diagram. Anyone who's heard me talk before knows that thermodynamics is never far away. This is a pressure enthalpy phase diagram. On the y-axis, and my cameraman here tells me he can follow me if I move, but apologies people online if I disappear. This is pressure on the y-axis, and enthalpy is on the x-axis. We normally see these as pressure temperature. However, as we'll see here, the enthalpy is very important for CO2. CO2 is a high enthalpy fluid, which means to understand it, we need to understand the enthalpy in the fluid. And enthalpy is just heat. On the left-hand side of this diagram, the solid line is the phase diagram. So on the left-hand side of this solid line, the CO2 is liquid. On the right-hand side, it's gas, and in the middle, it's gas and liquid. The green star here, this shows the wellhead conditions. Now, to inject into this well, your fluid must be at least 0 degrees or higher, because this well, like almost every well, cannot go below 0 degrees for integrity issues. The most vulnerable part of the well is usually the cement sheath, which is the cement that goes outside the last bit of well tubing and glues it to the formation rock. So we must stay above 0 degrees. So I've plotted with the green star the wellhead pressure and 0 degrees. And I've also plotted MP shipping and EP shipping, the enthalpies of these two. And what we can see very clearly, because enthalpy is on the x-axis, that the MP shipping is at a lower enthalpy than the wellhead, and the EP shipping is at a slightly higher enthalpy than the wellhead. This means that we can pump our elevated pressure ship directly down this well, and we will not breach the minimum temperature. We cannot do that without MP shipping. In fact, heating is required. Now, you may recall that we needed minimum facilities at this injection buoy, and so therefore we've got ourselves a problem. And the problem is that we need heating. Let's take a look at how much if we go to the next slide. It's about 100 megawatts of heating is required for this case. Now, this is because when we unload our shuttle, our ship, we want to unload quite quickly so that we can get that ship back to pick up the next load and bring in the other shuttle in place. This is a showstopper. It's impractical. We cannot put that much heating on a vessel. We cannot put that much heating on a buoy. We cannot get that much heat from our ambient seawater. And so therefore, we've been unable to show that MP shipping can work. And what's happened on this project? They had to drop the MP shipping idea, and the project has returned to the concept stage. They have failed in this case, in my opinion, to understand the true cost of the project because they didn't look at the full chain. They looked at the shipping in isolation without looking at how it interacts with those components at either side. One being the capture of the CO2, the second being the disposal. And in this case, it's the disposal is where they've run into problems. I have a second case study, and this case study is a port-to-port project. So if we go on to the next slide, please. In this case, we're taking our CO2, which is coming from a power station, and we're sending it to Scotland. Why not? This is fake, obviously. We do not have a massive gas turbine at the Pace CCS office, and Scotland is not currently accepting our CO2. We've got a lot of, a very large amount of CO2 being produced. This is a large power station. They don't have anywhere nearby for the CO2 to go. There is no route for pipeline export, and there's no local injection point, and so therefore they're relying on shipping for CO2 export. And this is in an industrial area, and so the harbour itself is quite busy. And so they're exporting via this existing harbour. And we've got our capture is obviously retrofitted onto the existing power station. What did this project assume? Because this project is also based on a true story. Well, they assumed LP shipping. Why? Well, we need the big ships. We've got loads of CO2. We want the economies of scale. We want big ships. So therefore, we get those economies of scale in our shipping process. Well, what did we learn when Pace looked at this one? Let's move on to the next slide, please. Firstly, and you probably guessed that a pressure enthalpy phase diagram wasn't far away. I have now plotted on here, I've got our elevated pressure shipping and our LP shipping. And the green star on this time is the enthalpy of the environment, air pressure, air temperature, ambient conditions. Now, this is a busy harbour, so they need storage at the harbour so their CO2 can go and be stored before it gets loaded onto the ship. If we have a release, then the CO2 needs to get to ambient conditions before it will disperse. When it gets released from our storage conditions, it gets really cold as we drop the pressure. Now, what we can see is that the amount of heat that needs to get into our CO2 is significantly lower for elevated pressure shipping compared to low pressure shipping. And this means, firstly, elevated pressure storage is inherently safer in a busy harbour. And as we have seen, the elevated pressure vessels themselves are much smaller because we have these pipes rather than big tanks, which means that the volumes are smaller as well. So we have a significant difference from a safety point of view at a busy harbour. And if we go to the next slide, we'll see what it looks like when we have a CO2 release. This is an example. This happened in 2015 in Germany. That is a CO2 truck. It's at MP conditions, and the valve was leaky. Now, the driver attempted to fix the valve and ended up with frostbite, but that was the only injury in this particular incident. But you can see the CO2 creating freezing fog, which shows you where it is. Freezing fog is where the CO2 is so cold it freezes water in the air, and you can see it hugging the ground. Now that CO2 will only disperse once it gets enough energy from the environment to disperse. At EP conditions, this is faster because less enthalpy is required. And at EP conditions, our storage tanks are much smaller, which means we're looking at less volume. There is a significant safety difference here. And that's not the only issue with this one. If we go on to the next slide, please. It's to do with the impurities. On this table here on the right, I've got the Northern Lights specification that they announced just a week or two ago, so February 2024. And their specification to get into LP or MP shipping requires a minimum of 99.81% CO2 with only 0.19% impurities. Now, the reason for this is that CO2, when it is cold, it is less capable of dissolving non-polar impurities. And our major impurities, and I've listed the 3 major impurities, are non-polar. If we have post-combustion CO2, we tend to have nitrogen when we capture it. If we have pre-combustion CO2, we tend to have hydrogen. And if we have capture direct from hydrocarbons, as in our LNG projects, we have methane. All of these are significantly more soluble at elevated pressure conditions compared to low pressure conditions. And in fact, we can have CO2 content of about 95% for our elevated pressure conditions. And you can see the amount of impurities that we can allow of nitrogen, hydrogen, and methane. Now, what this means is that we have now got more options for our capture process. Because we don't need the CO2 to be quite as pure, it means that it enables more technologies, and by enabling more technologies, it's likely to be cheaper. Of course, there's no liquefaction process needed. At our receival point in Scotland, if they have pipeline export, then we can just pump directly from EP conditions into the pipeline without heating it as well. And this is what I mean by an operability improvement, is that elevated pressure conditions simplifies things by allowing for simple transfer from capture to the disposal network. And if we go to my next slide now, please. And just to sum this up, this particular case study, we've learned that EP shipping is safer, it enables lower cost capture, and just like our first case study, it required a review of the full chain to understand the true cost of the project. This project is now reviewing its LP shipping assumption. And then finally, just to sum up, on the next slide, please. Thank you. And just going back to the beginning, this is a new industry. We are learning. Now, we've looked at about 15 CCS shipping projects in Europe and Asia. We've looked at about 100 projects in total around the world, so 15 with shipping. CCS is a new industry, and shipping is right now an emerging part of it. It is still very early days. When we started each of these projects, none of them had considered EP shipping, none of them. None of them had it as an option, none of them had it as a base case. After we've got involved, I can tell you that all of these projects have either adopted EP shipping as their base case or adopted it as an option. That tells the story for us. EP shipping is not the solution on all projects, but is absolutely one that can offer up significant advantages, as we've seen from a cost point of view, from a simplicity point of view, and from a overall full chain design point of view. Thank you.
Thank you very much, Matthew. We will now move on to the question and answer session. The moderator for this session is Mr. Naoki Watanabe, Deputy General Manager, Gas LNG Process Engineering Department Technology Engineering Division, Chiyoda Corporation. Mr. Watanabe, please.
Thank you for the introduction. I am Watanabe from Chiyoda Corporation, and I will moderate the Q&A session. Regarding the procedure, we will start by addressing the pre-submitted questions received at registration. Then we will invite the questions at the site and then from the online participants. We will post answers on the event homepage if there are any remaining questions. Now, let's begin with the pre-submitted questions. There are 2 questions. There is a movement within the EU-CEN, European Committee for Standardization, to establish standards related to CCS projects. In light of these developments from a standardization perspective, how should the transportation of liquefied CO2 be approached when you consider three methods of EP, MP, and LP, and factors such as the composition and properties of impurities in CO2? And next question is, what considerations should be made regarding the acceptance of CO2 for CO2 liquefaction at hubs from various emission reduction sources? We would like Mr. Tamagawa from Chiyoda Corporation to provide an answer. Mr. Tamagawa, please.
Thank you for the question. This time, I want to think about the standardization of liquefied CO2 from the perspective of liquefied CO2 impurities. For example, I understand that CO2 capture using amines is the primary method in those projects under Japanese Advanced CCS Projects Initiative. When the amine chemical absorption method is adopted, the purity of the recovered CO2 will be very high, more than 99.5%. In such a case, the effect of remaining impurities on the physical properties of CO2 is considered to be minimal. Given the risk of corrosion due to remaining impurities, it would be possible to establish a design basis for reducing them in each process in the value chain. Consequently, we believe that standardization would be possible. Also, I think it is possible to set slightly different conditions depending on the difference in standards of LP, MP, and EP, which was mentioned in the question. On the other hand, since amine chemical absorption is not the only method used outside of Japan, the emitter may send us the CO2 with multiple impurities and CO2 in multiple purities, and if we accept all of them, we will need new facility to remove impurities. At this point, we think we need to consider the case-by-case.
Thank you for your answer. Could Matt from PACE CCS explain the current developments in Europe regarding this question as well?
Yes, I'd be happy to, and thank you to our translators for helping me with the question. Things are, I guess, solidifying in the EU and around the world. There is an ISO standard 27913, which looks at pipeline transportation, and there is a specification which will be published in the next version later this year. And that will say 95 to 96% CO2 is normal for a pipeline project. Now, of course, that does introduce issues associated with the impurities, including corrosion, and of course it impacts how those fluids interact with shipping processes. I think the statement that it needs to be looked at on a case-by-case basis is very true. Every project is different, and while we can make general statements like we have today about the cost of shipping and what styles of shipping might make sense, ultimately the answer is different for every project depending on the source of CO2, the storage point, and the needs of from a regulatory perspective, from an operability perspective, and every other perspective in between. So there is still some way to go before we have consensus in the EU or indeed anywhere else.
Okay, thank you very much. I will now move to the second question. When will the LCO2 carrier in LP and EP be ready for service? Also, I have heard that more welding operators are needed to construct CO2 tanks for ships and onshore discharge, which makes the delivery time very long. How much impact do you think this problem will have if we are to consider CO2 vessels in the future? Please reply from NYK on this one.
Yes, NYK will answer this question. It is difficult to predict when the LP and EP LCO2 carrier will enter service. However, in terms of the construction period, assuming there are no obstacles, the vessels will be completed within approximately 2.5 to 3 years after the signing of the pre-contract for the shipping building construction. However, there are several situations in which this may be different. One is the availability of slots, or berths, at the shipyard. This will have a significant impact on when the vessel can be delivered. The other is the CO2 tanks. Currently the lead time for procuring these tanks is a bit uncertain, so if this is extended, the project's completion may be delayed accordingly. Therefore, if we consider completing construction in 2030 for example, it is important to decide the timing of the investment decision while considering the availability of shipyard berths and tanks and back casting with enough time to ensure a retractable schedule. From the perspective of a shipping company, we recognize procuring the Type C tanks for the carrier from Japanese or overseas tank manufacturers in China or South Korea would be very difficult because of the welding operator shortage. At present, there is a demand for tanks is mainly for gas cargoes such as LNG transportation, and if, in the future, the demand for ammonia tanks also increases, and at the same time, the demand for CO2 tanks increases further, the difficulty of procurement will become even greater in the future. I am concerned about this. I think the tank's production capacity will be a significant factor in determining when the vessels go into service. In addition, there is a general perception that there is a shortage of skilled welders, but this applies not only to tanks for ships but also to tanks on land, as mentioned in the previous presentation. Therefore, if we seek personnel resources for both ship and land simultaneously, I believe the impact on the construction period will be pretty large. In addition, welding is required to a certain extent to produce the EP cylinder tanks, CTCs. However, most of these tanks are derived from pipelines, and the manufacturing approach is quite different from conventional tanks. We know that the risk for CTC due to a shortage of skilled welders is relatively small.
Thank you. We only have a limited amount of time left. But from now on, I would like to invite questions from audience at the venue. We will limit the number of questions, but as we will hold the networking session afterward, if you are available, please feel free to ask questions directly to the speakers at the venue. If you have any questions, please raise your hand.
Thank you very much for your wonderful moderation, Mr. Watanabe. Also, we would like to express our gratitude to all the speakers who joined us today, to everyone who participated both on-site and online, and to NYK and Chiyoda Corporation for their support. Finally, I extend our thanks to the interpreters for their simultaneous interpretation services today. Now we conclude the Japan CCS Forum Technical Seminar.